Hello everyone, welcome to hopefully a new STK-ish tutorial by me. So I want to talk today about a little kind of side project I had called PoreMapper, which for the record will hopefully be merged into a new version of PyWindow, which will come soon, which is another piece of code that comes from the JavaScript. However, I just wanted to show PoreMapper because it is purposely built for visualization of the pores inside STK molecules. So we build a lot of cages with STK, and I've always wanted to be able to visualize the pore very easily, so I just wrote some code to do that. Basically, the way PoreMapper works is you provide it with a host. It then puts a very small sphere at the center of that host, and it inflates that sphere. So that sphere is called a blob. So we have I'll show the classes in the GitHub. So it's all available on GitHub, it's open there. There's some examples in the examples documentation, which I'll show in a little bit because I'm going to borrow the code from there. So you have a blob class. A blob contains beads, so a bead class. The host contains atoms. A bead is just a sphere. Atoms have their atom radii set based on the van der Waals radii of the atom type. So a blob contains beads, and as you increase the size of the blob, or the position of the beads expands out, they come into contact with the host. So then you get two classes. You have the blob, which continues to increase the size of the beads until a bead hits the host, and then it stops increasing. So your blob will kind of look kind of jagged. I might actually have, I don't know why I'm not showing this. I have an example kind of drawing of this, which is not very good, but you start with your blob of beads in the middle. It expands out. In red, the blob, as it hits the host, you see the blob contains beads that haven't hit the host, which expand outwards, shown here, whereas the blob also contains beads that have hit the host. The beads that have hit the host are put into a class called the pore, and the pore contains all the information we're interested in, and it's what we want to visualize, and it contains properties like its volume or its size, which are relevant for property prediction as well. So I've got a class of metal organic cages from my most recent paper on asymmetrical metal organic cage prediction. And I just wanted to visualize their pores for a presentation. I just thought I would show them as part of this tutorial. So this is again available on the STK examples GitHub. I will show the structures now. Hopefully they just load in PyMol. Beautiful. So if we look at, let's look at them one at a time. So we have 4D2, which is quite non-porous, but you can see its asymmetry. 5B4, which again is more porous but quite asymmetrical. 6A3 is a cage I think is really interesting. Sorry. Because it has kind of two distinct pores. And so PoreMapper is not going to be great at mapping this because it always starts from the center. But what it'll show is kind of the expansion of the blob outwards from this. And then 6C1, I don't want to show both, 6C1 is similar but a bit more extreme example of that. Cool. So let's write the code to do this, and then I'll show some PyMol visualization of these at the end. So starting with STK to load in the molecules, PoreMapper as PM time, because I just want to show how quick it is, and then glob to read in all the files, so we can import this. We have our 4 files there. So for mol file in mol files, we will first use STK very cheekily. So PoreMapper just needs XYZ coordinates. So we need to convert these to XYZ files. So if we actually go to the example and we go to, I'm going to show 2 examples here because there's 2 different things that PoreMapper can do. PoreMapper can, if we look at run the calculation, it can the calculator is called an inflator, but when you run it, you run either inflate blob, which does it in a stepwise fashion. So you can output the properties of the blob and the pore for each kind of incremental inflation of the blob. And this might be useful for mapping these properties as a function of blob size. However, what we actually want is to just get the inflated blob, so to get the final product. So this is the code we want to copy. I'm just going to copy all of it, and then once we have it all, I'll talk through each point. So if we just Control C, copy that into here, that should basically work. But as you can see, we want to init our host from an XYZ file. So we need XYZ file equals molfile dot replace dot mol with dot XYZ, and then we'll go stk dot building block dot init from file mol file. So that will read in the mol file, and then we'll write out the XYZ file. Cool. And then we should be able to run, I'll run through each line of the code. We should be able to do this because we'll have the XYZ file, although we should change, obviously, the path to be XYZ file. We, just for kind of consistency, we move the host to that a centroid of 000. We then, or to the origin, that makes more sense. We define the calculator. We'll use for each bead, we'll use a radius of just 1.0. Obviously, this sets the resolution of your calculation, but also kind of the physical nature of the calculation. If you set this to, say, the Van der Waals radii of hydrogen or helium or nitrogen, then you get a more physical outcome. However, PoreMapper is not designed to be physical. It's in itself very simple code for visualization. So let's use a value of 1.0, start timer, and we'll get the final result from calculator.getInflatedBlob, input the host, get the output time from the final result. So the calculator spits out a result class. The result class contains the pore. The pore contains the blob. And this is a kind of a weird way to think of it because you get the pore from the blob. But from a class design perspective, it's better if the pore actually contains the blob and you get that out there. You can also calculate the windows from the pore. So this is actually a calculation on the blob. But the windows correspond to the points or the beads of the blob that did not hit the host, and then it does some clustering to calculate the number of windows. And this is just a bunch of prints, so it'll print in the final step. I didn't talk about the actual algorithm, but it's described in the README. So we actually don't care about this information. We just want to see the blob, the maximum diameter of the blob, the pore diameter, or radii in this instance, the pore volume, the number of windows, the window size, the different window sizes, and then the asphericity and shape anisotropy talk about how spherical the pore is. So it'll print that for each structure, and then we also want to output the pore and host and blob and host structures. So we'll get rid of this, and we will just set this to be XYZ file dot replace dot XYZ is final dot XYZ. I'm going to copy this. So we'll go final, this is the blob, and this is the pore. Cool, so if we just run this, bug, awesome. Yep, so typo, nice work. Prefix is not defined, where have I defined? Yep, doing more file. Cool. So, let's look at the output. First, PoreMapper itself outputs some information about when it broke. So, as the blob inflates, if all of the points of the blob hit the host, it stops the calculation, and it will either tell you that, or it'll tell you that it's popped, i.e. the blob has hit the maximum diameter of the host, and there's no point going any further. The runtime is 0.7 of a second for this system, 0.6 of a second for this system, milliseconds for the other two, because you'll see it's breaking at step 1 with no more movable beads. So the cages are too non-porous for PoreMapper to map the pore, which is interesting. Further going down, the final result gives you all this information. The blob has 854 beads, the pore has 833. So the difference here is that there are 21 beads that make up the windows, whereas the rest have hit the host in some way. And then you've got all this information. There's 3 windows, they have a range of sizes. Values of 0 for the asphericity and shape anisotropy correspond to spheres, so these are slightly non-spherical. And then the radii and volume are useful for whatever you're trying to do. Cool, that works. Let's do some visualization because that's what we're here for. So let's just load in all the XYZs. And it's going to be slow originally because there's a lot of points there. So let's hide everything. And let's just pick one of the structures, and that's all I'll do for this video, and then hopefully that's shown you everything you need to see. Cool. So let's get the cage structure up. Let's go sticks. Zoom out. How do I do that on a keypad? There we go. Sorry, I'm not great without a mouse. Surely there's a better way to do this. Alright. There we go. Fantastic. Cool. So let's show the blob as a mesh and the pore as a surface. And let's color everything by object so that we get a distinct blob. And you can see, actually, if we now orient with this, you can see that kind of makes sense. The blob has gone out this kind of 2 windows here and here. Let's do a background white. And you can see where the kind of windows would be, and you can see that the hydrogens here and here are going to block this other window. It's quite a non-porous structure. Then if we actually look at the pore, it fits nicely in the middle. So that would be a nice visualization of the porosity of the structure. Run Ray, and I think that's, for 5 seconds worth of work, that's quite pretty, and it's useful for potential analysis as well. Just because it doesn't take long, let's do one more structure. So let's get this structure loaded. Hopefully it's one of the non-porous ones. One of the porous ones. Actually, so we'll show this as a mesh again, and show this as a surface. Oh, that mesh does not look good in white, so let's just... So you can see there's this large pore in the middle, and then multiple windows coming out. You can see where you might have to play with the resolution here, where it's kind of not reproduced on the other side, and so there's some finickiness with thresholds here, but we can then plot the pore, and it looks like what it looks like. It's not perfect. A PoreMapper is not meant to be perfect, but it's nice visualization that you can do. Just for clarity, I will show for one of the non-porous ones, the structure, and then the blob, which you'll see starts in the middle, and then there's no way for it to go, so calculation stops. Anyway, thank you for listening. I hope this has been helpful, and let me know if you have any questions. and I'll help out. Thank you very much.